Okay, next up, we have MAR assessing through physical models, comparison of laboratory and field experiments. Jana Sallwey from Germany. Excellent.
Okay.
All right.
A lot of technical. Yeah, so my name is Jana. I'm a part of the Innovas group at TU Dresden. And we already presented a lot of web tools at this conference, but we did also do some laboratory and field experiments, and I will focus on the comparison of these experiments that we did over the past years. Okay, so why did we do this? Why did we do a lot of experiments that basically did the same? We looked into the issue of scaling, and specifically we looked into laboratory experiments and small-scale field experiments. Experiments are often done because you want to get some deeper process understanding, or you want to do some controlled experiments that you cannot take directly to the field. But there's often a problem, and I picked some literature resources that exemplify this. So there's often a call for like a strategic approach, or the literature says that it's not really clear what happens when we take these laboratory results to the field, because there's often an offset. And if you go further into literature, you find a lot of resources where it's even depicted where the problem is. So some of the rates will be a lot higher in the field than in the laboratory. You will miss out some processes, as mentioned here, or you might not find the main trends. So we thought, okay, let's have a closer look at this and why this is happening. And we built up an experimental setup, you can say, that consisted of 3 different experiments. We have here we have a field site that is located at our research institute with an infiltration basin. The size of the basin is roughly 1.35 meters times 90 centimeters. Then we took this experiment, we reduced it by a factor of 3 and put it into the lab. So we have here a stainless steel tank that is basically the same experiment as outside, just taken to the lab. And then we reduced this experiment even further in a dimension. So we have a column that is the same height as the tank. And all 3 setups were run under almost similar boundary conditions. We ran a couple of scenarios. This is not all of them, but this is a selection. We changed the soil throughout the experiments to see what influence this might have. So we used a sand and then a slightly siltier sand in the second set of experiments where the infiltration capacity was reduced. We worked with different hydraulic loading cycles, but we kept the hydraulic loading rate constant. Well, we wanted to see the influence and if this is represented in all scenarios. And in the field, we worked with different climates, which we could not really avoid. Germany is quite strongly influenced by seasonal variability, so we looked into this further. I will not present that today. A colleague of mine did that. But we kept the lab scale units. We kept them at a constant temperature and humidity, but we compared this to the field to see what influence does that have. Okay, so what did we find? These are some results comparing the tension measurements. In the graphs, you always have the laboratory measurements, so here for the tank, and then overlain are the field measurements. This is tank column. Then we have different scenarios. We have soil type 1, soil type 2, and we have also results from different depths, so in 30 centimeters depths and 70 centimeter depths. And there's a lot of information here, just maybe to point out some of the main things. For all experiments, we can see that it's reacting quite strongly to our infiltration cycles, so we can really see the rapid decrease, we can see the rapid increase, and we can see a steady wetting phase and a relatively steady drying phase after the rapid decrease. So this is at least positive. We can say, okay, all systems represent this. Now the negative part is that we see that there is a very strong variation in terms of quantitative assessment. So both systems, the tank and the column, always showed values that were, now we're talking about tension, they were always below the field. So both of our laboratory systems always brought us values that were wetter than the field one. This is especially true for the column, so the column really is a lot wetter than the tank. And we have the same is happening for both soils. So it's not just one soil and we cannot reproduce it, but it's for both soils this happened. And to get a closer look, because this is maybe a little bit confusing, we picked out some key points. So we looked at the minimum tension during the wetting phase and the maximum tension during the drying phase and depicted them. So it's a bit easier to see. And what we can find is that these are this is during the wet phase. So during the wet phase, the tank and the field, they're actually quite similar. They even produce the same trends. So the tank works relatively well to reproduce the wetting phase of these cycles, whereas the column is sometimes more than 2 kilopascals further down in the tension measurements, which is of course due to the 1D character of the soil column, and there's no lateral water flow. So this is somewhat expected, but the difference is still quite astonishing. And when we go to the drying phase, we can see that actually the tank and the column, they are quite similar, and the field is draining much stronger. So we have quite bad representation of the drying phase in both systems. We account this to our lower boundary condition. Both systems were operated with a drainage layer, and we could sometimes find that there was a capillary barrier developing, so this might be the case here. Okay. Okay, so usually you are not really doing these experiments to just see the water content in the column, but what's more interesting is to look into clogging processes. So this is just one of the results that we did. We also did some tracer tests, but I'm not going to show this today. But this is maybe very representative of the problem that we might face when we do these experiments. So if you look at the column, which is depicted in red, we can see that the arrival time of the wetting front, this is now in 70 centimeter depths, it doesn't evolve over the course of the 2 experiments that are depicted here. So if you would look at this without these graphs, you would say, okay, for this experiment, there was no clogging. And yeah, so the system operated well, whereas actually the column we had to abort the experiment here because there was overflow, so it was definitely clogged. At least in the field and the tank there is a difference, but we can see the arrival time is increasing, so we can, we see that there's clogging happening. But if you just saw the column experiment, it might actually be misleading to see these results. And the second parameter that we looked further into was the oxygen saturation. We don't have any field data here, which is, we just couldn't implement that in the field at the moment where it was built. So we're just comparing the tank and the column. And we can see here in this scenario that we have a longer drying time, and here is a shorter drying time of just 6 hours. And both systems, they show that with a shorter drying time, we reach more steady oxygen saturation in the system, whereas with the longer drying time, we have a much further decrease of oxygen saturation, but still with both systems, the recovery is quite good. So the trend can be represented by both systems, but the decrease, so the quantitative value is really quite different, and it becomes even clearer when we look at or compare it in two different depths. So we can see that in the tank we have a relatively steady oxygen concentration in both depths, whereas in the column the oxygen saturation varies greatly. For us now it's a bit hard to say, okay, what would be more representative. It's actually also a big discussion in our working group. If you have a big infiltration basin, would the column be more representative that shows much stronger oxygen decrease? Or would you have the tank which has the lateral inflow of oxygen on the side? Because in a big infiltration basin, you don't really have this lateral inflow in the center of the basin. So this might be what's happening in the center of a big infiltration basin, and this might be more representative of the sides of the infiltration basin. So it's a bit hard to say what's correct here. Okay, in conclusion, what we could see from our experiments is that we have a similar flow behavior in all of the systems. So you can do some qualitative assessment, this will be possible, but to do a quantitative analysis is kind of hard to do with both systems, even though the tank gave closer results to the field than the column, it still shows a lot of variation. We looked at the differences and looked if these differences between the tank and the field and also the column and the field, if it's consistent over time. So you kind of could calculate let's say a linear equation or a threshold value that you could add to the lab values if this was known, to adjust them to be more close to the field. And it worked relatively well, so this could be done, but still you would have to have a set of field and laboratory experiments with the same set. So it's maybe a possibility. And for the oxygen transport, it's the same problem. We have a qualitative behavior that is very similar, so this can be done by the experiments, but to get really down to the values and say, okay, this is the oxygen level that we're reaching is quite impossible with these setups. So that was it. If you want to read more about it, you can go to our website, and we have some more information on the experiments and what we did. And thanks for listening.
Really nice job. Thank you very much. How about some questions?
Excuse me?
Oh, yep. Go ahead.
My name is Ahmed Hadidi from Oman. Mm-hmm. So my question related to the hydraulic conductivity of the soil. So mm-hmm. Did you apply any pressure, any compaction for the soil? Because this might affect the hydraulic conductivity. Did you take that into consideration? For example, having two columns with different pressure or something like this? Thank you.
We did. When both the column and the tank, when they were packed, and even the field, because the field we also put in the same soil there, we calculated the density of the soil. So it was roughly in the same area, but it was practically not possible because in the field we used a compaction machine, and in the lab it was done by just a person. By hand. So in the end, we ended up with different compactions. It was still hard to quantify that for us, but that definitely has an influence. Yeah.
Good. Another question?
Kasimov, also from Oman. You mentioned capillary barrier. Can you please elaborate? Maybe terminology is different from what I understand as a capillary barrier, which is effective at very low infiltration rates, right? So for unsaturated condition, but you have ponded infiltration basin. Where is the capillary barrier?
We think that it developed because we had a gravel layer on the bottom of the. Maybe our definitions are different.
This is what.
Right? So
what is your definition of capillary barrier?
So we have a gravel layer at the bottom of the tank and also of the column, and above we have the sand that we used. And there is capillary barriers are evolving when the difference between the gravel or the two soils that you're using, or the gravel and the soil, is too big. Then the water doesn't infiltrate into the gravel directly, right? Because it has
only for low infiltration. Only for low infiltration rates, right? So if you have saturated conditions,
yes.
and you have permanent, right? So it's a steady state flow practically, right? So
no, we didn't.
I mean, so it's almost saturated, right? So periodically, right? So.
We did have periodic infiltration, and we didn't observe this behavior, for example, when we did continuous infiltration. We also had continuous infiltration tests, and there we didn't see any of this behavior that the lower layer was wetter than we expected. But it happened a lot with this periodic infiltration, that we observed that the lower layer in the systems was much wetter than we expected that it would be. So we think that there's like this ponding on top of the gravel layer, and then there's a breakthrough at some point, and then it flows freely into the drainage.
Any other questions? Still got some time. Quick question. Did you think about cycling, because particularly a lot of us in colder latitudes, a lot of our recharge will happen in the winter time or springs, and we get that diurnal flux in temperatures. Mm-hmm. The field, the lab experiment, did you play with temperature? You kept it constant in the lab? You did?
Yeah.
Okay. Because it is fascinating for viscosity and things like that when we get really cold at night in the winter. Yeah.
I think we discussed to do a lab experiment where we have hotter temperatures to see if there's more clogging. I don't actually know if we did it in the end, like one of the last ones, but we really wanted to keep these experiments steady.
Sure.
To have this as a boundary that we don't have to regard.
Yeah.
Because there are so many other influences, and you don't want to. You want to rule out.
You could go forever. Yeah. Yes. Want to finish the degree. Yeah. Okay. Thank you all. And if there's no more questions, I guess we're just ticking right along here.